So, welcome everyone. What we're going to be looking at in this set of videos is chemical formula. How to go from the name of a chemical to writing a chemical formula. So by a chemical formula, we mean using the element symbols and numbers to represent the ratio of different atoms to one another within that chemical. So for example, H2O is water, and that means it has 2 hydrogen atoms for every 1 oxygen. And you'll note that the symbols are represented in capital letters, sometimes a capital letter with a small letter beside it, and the numbers that show whether or not how many there are of that chemical are written in small to the right hand side. So that's a 2 for H2O. If a symbol doesn't have a number, then what we have is 1 of that element. So this set of videos is going to be about writing chemical formula. And specifically, in this video, we're going to be looking at the first 3 types. We're going to be looking at writing chemical formula that have clues in the name that allow you to just write the formula without having to look up the periodic table, apart from maybe to find the symbols. Secondly, we're going to look at using valency. And thirdly, we're going to look at chemicals that have Roman numerals in the name. The second video that I'll make on chemical formula will look at the more complicated ones, chemicals ending in "ite" or "ate, and also at ionic formula. So firstly, what we'll do is clues in the name. Now, clues in the name, what we are looking for and what we mean by clues are, does the chemical name contain mono, sometimes just mon? Does it contain di? Does it contain tri, tetra, penta, or hexa? Now, if these feature anywhere in, sorry, I spelled tetra wrong there. Tetra, penta, or hexa. If those feature in the name, you should be able to, just looking up the symbols, be able to write out the chemical formula. And that is because mono, if that is in front of part of a chemical name, that means that there's 1 of it. Di, 2, tri, 3, tetra, 4, penta, 5, and hexa, 6. Now where we have this, we typically have 1 chemical that doesn't have a clue and 1 chemical that does have a clue. So a good example is carbon dioxide. Now carbon doesn't have a clue, so there's no clue, and this one has di. Now if there's no clue, that equals 1 always. If there's no clue, there's 1 of that element. And di, well, we know from here, di equals 2. Then what you do is you use your data booklet, and if you use the data booklet page 7, page 7 has a list of all the elements down the sides, and if I can hold it straight, the next column is the symbol. So if we look up carbon, the symbol is C. Dioxide, oxide means it's coming from oxygen, and oxygen symbol is O. There are 2 oxygens, So we do CO2. Another good example, phosphorus, pentachloride. Well, phosphorus pentachloride. Well, this one, there's no clue in phosphorus, but we've got penta here. If there's no clue, that equals 1. And penta, well, penta's here, penta equals 5. So we can just write out the name by looking up the symbols. Phosphorus has P, and chloride comes from chlorine, and that symbol is Cl5. So you can see, even if there's only one clue in the name, beside one of the parts of the formula, parts of the name, you can write out the chemical formula. So the chemical that has no clue in its name, the symbol is just written out on its own. There's only one of them. So that is how we do the first type. Chemicals that have clues in their name. And you can see that's really straightforward. The second type is where we use valency. Now valency, what valency means is the number of electrons an atom must lose, gain, or share to obtain a stable structure. And that's a stable electron structure. And that's usually a full outer shell. Usually a full outer shell, which is 8 electrons. Now if you do a full outer shell with 8 electrons, that might seem quite complicated, but it's actually quite easy. So if we look at page 6 of the data booklet, and we see that the groups go from group 1 to group 0, so they've left out the transition metals, and that's important. So if we look at the groups without the transition metals, we have group 1, 2, 3, 4, 5, 6, 7, and group 8, which is sometimes called group 0. The valency for these follows a really easy pattern. Valency goes 1, 2, 3, 4, 3, 2, 1, 0. So groups 1, 2, and 3, and group 4, valency is the same, but then it just counts back down. 3, 2, 1, 0. Now what's happening here in groups 1, 2, and 3 is that that's the number of electrons they lose to get a full outer shell. Group 4, that's usually the number that it shares. And then groups 5, 6, and 7, that can be them losing or sharing those electrons to get a full outer shell. And group 8, or group 0, has a valency of 0 because it already has a full outer shell and does not need to form bonds. And so usually these don't form molecules. So with valency, ignoring the transition metals, we consider groups 1, 2, 3, 4, 5, 6, 7, 8 as is represented on page 6 of the data booklet. 1, 2, 3, 4, 5, 6, 7, 8. And the valency goes 1, 2, 3, 4, 3, 2, 1, 0. And what we're going to do is we're going to show how we use valency to obtain the formula. But there are an important rule. So the rules for when you can do this is, the first rule is that the chemical must end in IDE. So it must end in IDE, but not be hydroxide. So even though hydroxide ends in IDE, this rule that I'm going to teach you only works if it ends in ide but is not hydroxide. And the rule, what we do is we do a set of letters S, V, S, D, F. And we're going to do that every single time. Now that stands for symbol, valency, swap, divide, formula. So let's start with a chemical, magnesium chloride. So magnesium chloride. Now we're going to do symbols. The symbol for magnesium is Mg. The symbol for chlorine is Cl. Now, this is where we need to look at the data booklet. Magnesium is here. It's in group 2, and we know that the valency of group 2, the valency is 2. Chlorine is in group 7, and valency goes 1, 2, 3, 4, 3, 2, 1. So valency is 1. Now this is where we do something important, and we swap the numbers. So the 1 from chlorine swaps over to magnesium, and the 2 from magnesium swaps over to the chlorine side. Now the divide, what that is for is, can these numbers be divided to make anything simpler? In this case, we can't do anything. Because 1 can't make 1 any simpler. So we just keep the numbers the same. 1 and 2. Now what we're going to do is we're going to write the formula. And what we do is we take the symbols down and we write the numbers beside, well, on the right hand side at the bottom beside the symbol that it's now underneath. So magnesium has 1. We know that we don't include the number 1 in a formula, so we're just going to write magnesium. Chlorine has a 2 underneath it, so we write MgCl2. Okay, so we're going to do another example, and we're going to do silicon oxide. So silicon oxide, we're going to do the same. We're going to do SVSDF. Now if we use the data booklet to look up the symbols, silicon has the symbol Si. Oxygen for oxide has a symbol O. Now if we find silicon, silicon's here, it's in group 1, 2, 3, 4, and valency goes 1, 2, 3, 4. So the valency of silicon is 4. Oxygen is in group 6, it's here, and valency goes 1, 2, 3, 4, 3, 2. So oxygen has a valency of 2. Now we swap them over. Now we look, can we divide? Can we simplify that down? Is there a number we can divide both things through? And we can. We can divide both of these numbers by 2. So we can divide both by 2, and what we end up with is a 1 and a 2. And now when it comes to writing the formula, again, we write the symbol, look at the number underneath it, and that's what we're going to put beside it. If the number is 1, we leave it out. So when we're writing our formula, we've got silicon, there's 1, so we don't write a number. And then we've got oxygen, there's a 2, so we write the number 2. That's quite straightforward. So remember, symbol, valency, swap, divide if you can, then write the formula. Now, on this page, where we were looking at valency 1, 2, 3, 4, 3, 2, 1, 0, we left out the transition metals. And that's because transition metals, they can have valencies that change. And they use Roman numerals. For valency. So, for example, iron 2 chloride, cobalt 3 fluoride. If we've got a transition metal, these things in Roman numerals, and they're usually capital Roman numerals, so you might see them like that, or just the lines, they tell us the valency of the transition metal. So I or I equals 1. II or II equals 2. III or capitals equals 3. IV or equals 4. V or V equals 5. And VI or V equals 6. So that's what you need to do. Now, once you've worked out what the valency of the transition metal is, you just follow the same procedure as before. So we'll do a couple of examples. The first one we'll do is iron 2 chloride. Now we do the SVSDF method. Now the symbol of iron, if we look up the periodic table, is Fe. The symbol for chlorine is Cl. Now from the Roman numeral here, we know that the valency of iron is 2. Now chlorine, we need to use this. Chlorine is in group 7, and the valency goes 1, 2, 3, 4, 3, 2, 1. So the valency of chlorine is 1. We then swap. We cannot simplify that, we cannot divide that. So we keep it as a 1. We keep that as a 2. And then what we do is we write the symbols underneath. So iron, symbol is Fe. There's a 1 in the column, so we don't need to write anything. Chlorine, we write the symbol, the number, the bottom is a 2, so we write a 2. FeCl2. Now the next example and the final example, we'll do iron 3 oxide. SVSDF. We've got SVSDF, so just like before, the symbol for iron is Fe. The symbol for oxygen is O. Now this time, we've got III, and that means the valency is 3. Oxygen is in group 6. Here, valency goes 1, 2, 3, 4, 3, 2. So the valency is 2. We swap. 3 and 2, there's nothing we can simplify that to, so we keep the numbers where they are, and then we write out the formula. So Fe, there's a 2 underneath it, so we have Fe2, and let's try and get all of that fit in, Fe2, and then we have oxygen, and with a 3 underneath it, we write a 3 to the right hand side. So Fe2O3 for iron 3 oxide. So what we've done today in this lesson is we've looked at writing chemical formulas if there's a clue in the name. Then we've looked at using valency from page 6 in the data booklet. And then we looked at transition metals where they use Roman numerals in the end. So the first one, where we had clues, the clues you're looking for are mono, di, tri, tetra, penta and hexa. And if that appears, that tells you exactly how many of that element there are. If an element does not have a clue, and the other one does, the one without a clue has 1. We then looked at using valency, and we note that we can only use this for compounds that end in IDE, and the exception is hydroxide, where we have to do something else. We looked at the method, which was to write the symbol, the valency, swap the numbers over, divide if we can, and then write the formula. And then we learnt for transition metals, if we use transition metals, they have to have the valency shown in Roman numerals after the name of the transition metal. And once you've seen that, you can use it to write the valency and do the exact same method as before. So that was part 1 of writing chemical formula. I hope that made sense to you, and see you next time.